Welcome to this expert-level explanator of the F-35B Lightning II. We're doing a systematic subsystem teardown using only verified technical documents and engineering schematics. All right, let's dive right in. To keep things organized, we've broken this teardown into 4 engineering pillars. We're looking at propulsion and stovial mechanics, flight control and actuation systems, the power and thermal management system, and finally, structural integrity and low observable design. Let's kick things off with Section 1, Propulsion and Stoval Mechanics, where we'll focus entirely on exactly how this jet generates vertical lift. We have to begin at the very heart of the aircraft. This is the Pratt & Whitney F135 engine architecture. Now, notice how cleanly this architecture is divided into 2 primary sections. Over on the left, you've got the cold section. It kicks off with air that gets heavily compressed before moving into the hot section on the right. This is where jet fuel mixes with that compressed air in the combustion chambers, burning at over 1,000 degrees Fahrenheit. That drastically spikes the air's kinetic energy before it's forced right out through the low observable asymmetric nozzle at the tail. But here's the real question. How does all that forward thrust actually translate into vertical lift? Well, the F-35B achieves a totally revolutionary lift-thrust ratio of 1.5 to 1. If you trace the power extraction here, you'll see power is pulled directly from the main engine's low-pressure turbine. There's a closed-loop dry disc plate pack clutch, which actually leverages aircraft brake technology, and it fully engages in under 9 seconds. Once that happens, a driveshaft transfers a staggering 29,000 horsepower straight to a counter-rotating lift fan sitting right behind the cockpit. That single unit alone is pushing out about 46% of the total lift needed to keep the jet stabilized in the air. So you've got this massive downward force, right? The crucial point is how it's actually controlled. Thrust modulation from the lift fan is handled by variable inlet guide vanes right at the top of the fan. Meanwhile, tucked underneath is the variable area vane box nozzle, which takes care of fore and aft vectoring. This box uses 6 highly cambered vanes driven by dual tandem hydraulic actuators, and get this, it can rapidly vector the exhaust thrust in a 41.75 to 104 degree arc at a rate of 40 degrees per second, literally pointing the thrust exactly where it needs to be instantly. Now, perfectly balancing at lift fan up front is the 3-bearing swivel module, or 3BSM, at the rear. When you look at the 3BSM highlighted here, it is just an absolute marvel of engineering. It seamlessly deflects the engine's primary exhaust flow through a 95-degree pitch axis, all without changing how the main engine operates. When it's pointed straight down, it's vectoring up to 23,900 pounds of thrust. That gives us the other massive column of air needed to perfectly balance the jet during a vertical landing. Okay, let's transition to Section 2, Flight Control and Actuation Systems, and see exactly how the jet builds on that propulsion architecture to precisely focus on directing the thrust. The sheer ingenuity of the actuators moving that massive rear nozzle is just mind-blowing. Instead of relying on traditional heavy hydraulic fluid systems, the F-35B actually uses pressurized jet fuel as its hydraulic fluid. It's a concept known as fuel-draulics. Twin fuel-draulic actuator motors power the bearings of the 3BSM, and crucially, they are designed with a fail-degraded capability. What that means is, if an actuator motor completely fails, the system automatically guarantees full torque at half the normal rate. It's exactly this built-in redundancy that allows a pilot to execute a perfectly safe shipboard vertical landing even after a primary mechanical fault. Now, to keep the aircraft from rolling left or right, main engine fan air is redirected outward to roll posts in each wing. These are controlled by twin-motor rotary actuators. The Lockheed Martin technical documentation states these roll posts contribute about 10% of the total vertical thrust, but the CDN document states it's about 8%. The primary takeaway, regardless of the 2% difference, is that without them, the jet simply could not stabilize its roll axis during a hover. As you can imagine, generating and vectoring tens of thousands of pounds of thrust creates some immense thermal loads. That brings us to Section 3, the Power and Thermal Management System, focusing entirely on managing megawatt heat loads. Check out this integrated GIS-IST architecture. The F-35 essentially combines what used to be entirely separate systems, auxiliary power, emergency power, and environmental controls, into one highly integrated package. While in flight, engine bleed air drives the refrigeration cycle, and this architecture doesn't just keep the pilot comfortable. It is explicitly designed to cool high-powered avionics and manage the massive thermal loads of potential future directed energy weapons. The thermodynamic backbone of all this is a closed-air reverse Brayton cycle. The math behind this closed loop is elegantly straightforward. Heat gets absorbed from the aircraft's internal thermal transport bus at lower temperatures. We see that represented here as QTTB. Then, that air is compressed and released directly into the engine bypass flow at higher temperatures, represented as QBy. It's just a brilliantly efficient closed loop. So where does all this heat actually end up? Well, waste heat flows from the computers and avionics, travels through that transport bus, and gets rejected directly overboard, right into the engine fan duct air. This is huge because it entirely eliminates the need for those drag-inducing ram air scoops on the outside of the jet. And for a secondary heat sink, the system actually pumps heat into the onboard fuel tanks. Remember a few minutes ago when we talked about how the fuel acts as a hydraulic fluid for the nozzles? Well, that exact same fuel is pulling double duty, acting as a vital thermal heat sink for the electronics. Finally, we've reached Section 4, Structural Integrity and Low Observable Design. This is where we look at packaging the system. We have to understand how this incredibly dense network of propulsion, actuation, and thermodynamics is packed into a stealthy, structurally sound airframe. To maintain that low radar signature, the airframe uses some highly specialized structural elements. Take the diverterless supersonic inlet, for example. It uses a forward-swept cowl and a specially shaped compression surface to feed air to the engine without using traditional radar-reflecting boundary layer diverter plates. Back at the rear, the main engine nozzle uses serrated trailing edges and tight seam control to keep radar reflections to an absolute minimum. But the most fascinating part is how internal components pull structural weight. Those heavy sidewalls of the lift fan vane box we looked at earlier, they don't just hold the vanes. They are literally airframe mounted and serve as integral structural keel members for the aircraft itself. Ultimately, the F-35B represents an absolute masterclass in multi-role integration. It constantly leverages single systems for multiple uses, like the fuel being used for both hydraulics and cooling, or fan sidewalls acting as structural integrity. But it really leaves us with a pressing engineering question as we look to the future. As electronic payloads and directed energy weapons push aircraft thermal requirements into the megawatt range, how will these closed-air thermodynamic cycles scale up without eventually starving the main engine of the air it needs for thrust? It is a huge challenge. Thank you so much for joining me on this explainer. I really hope this structured teardown brought some clarity to the brilliant engineering behind the Lightning II.